Welcome to 1-6, Properties of Real Numbers. In your Know It notebook, this is going to be pages 13 and 14. We're going to start with a vocabulary term, which is counterexample. A counterexample is an example that disproves a statement or shows that it is false. Remember, if I don't give you enough time to write the term down, you can always pause the video. Today we're reviewing properties, all those ones that are so easy to forget. First one, commutative property. Notice there's no N in there, not communing. It's commutative property. When you add real numbers, you can add them in any order. You can multiply real numbers in any order. So the order doesn't matter. That's the big thing about the commutative property. It's really telling you that order doesn't matter. So I like to think about commuting to and from school, right? If I decide to stop and do a couple things along the way, it doesn't really matter because I'm still going to end up here at school. Algebraically, we can say A plus B equals B plus A, or multiplying, and we've got a few numeric examples here too. So the big thing to remember here is that order doesn't matter. That is some bad writing on my part. Let's see if I can get that to look a little bit better. Order doesn't matter. Today appears to be a sloppy handwriting day. Next up, we have the associative property. Okay. And the key to the associative property is to know that when you are adding, changing the grouping, changing what numbers are grouped together with parentheses, does not change the sum. When you're multiplying, changing the grouping will not change the product. So this one was all about grouping. Okay? Commutative is all about order. Right? Associative is all about grouping. I find it easiest to remember this, that a group of people you hang out with is the group of people you associate with. So try and associate those two words together, grouping and associative. There's a couple examples there at the bottom, right? And on your Know It notes, you should be writing the words, the algebra, and the numbers. And I'm just noticing here there aren't any algebra examples, so I'll put some in for you, right? So if I say A plus B, and I want to do that first, then add C, that's the same thing as if I do A, but before I add it on, I do B and C. Okay. Multiplying, I can multiply A times B first, and then multiply by C, or I can first multiply B times C and then multiply by A. It doesn't matter. Notice though all the operations are the same here. Next up, we have everybody's favorite, the distributive property. I'm not going to write the distributive property down in words because it is so long, right? The distributive property basically says that the product of the sum is the same thing as the sum of the products. So numerically, right, it doesn't matter whether you add B and C first or whether you first multiply each of them by A. You guys have done lots of this last year. Your teachers swear to me that they have taught you how to distribute. Remember, you're going to take the A from the outside, right, and it goes multiplying by both its friends inside the parentheses, so that you end up with AB plus AC. Okay, it works for subtraction also, okay, because remember that, of course, subtracting is really just the same thing as adding a negative. Numerically, right, It doesn't seem necessary for things as simple as 5 times the quantity 1 plus 2, which obviously would make the most sense to just do 5 times 3, right? But you could, if you want, do 5 times 1 plus 5 times 2 and get 5 plus 10 is 15. Now it makes more sense on ones that are a little more challenging, like 3 times 108, because there we could do 3 times 100, right, plus the 8, and we can then do each of those operations in our head really easily. 3 times 100 is obviously 300, and 3 times 8 is 24, and add those together to get our grand total of 324. The last one is the one that you're the least familiar with. It's this idea of closure. And what closure means, you're going to go back and put this on the vocabulary part on page 13. What closure means is that when you do an operation on two numbers in a set, and by a set I mean like the set of real numbers, which is pretty much all the numbers you ever deal with, or a set of a smaller set like the set of integers or set of whole numbers. Closure tells us that when you do an operation on two numbers in the set, the answer is also in that same set. For addition, we can say that it's closed for whole numbers. When you add two whole numbers together, your answer is still a whole number. There's not any whole numbers out there that you add that you don't get another whole number. Okay. Subtraction, though, is not closed. If you subtract two whole numbers, sometimes you get a whole number. Like if you do 8 minus 3, you get 5, which is also a whole number. But you don't always get a whole number because you could subtract a bigger number from a smaller one and end up with a negative number. And negative numbers aren't whole numbers, they're integers. Okay. So now's a good time to bring up that idea again of counter examples. Right? A counter example disproves something. So if we want to try to think of a counter example to disprove the statement integers are closed under division, we would think of two integers that we could use that wouldn't give us an integer answer. So let's see if we can think of one here. Like if I do 10 and negative 2, I get negative 5. Well, negative 5 is still an integer, so that's not a good counter example. Right? But what if I do negative 2 divided by 10? Right? Now, when I divide, I get negative 1/5, or negative 0.2 if you want to give it as a decimal. And that is a rational number, but it's not an integer. And so that is a counter example. Right? It shows that integers are not actually closed under division. What the closure property actually says here, right, is that the real numbers are closed under addition, subtraction, and multiplication, but not under division. So when you add two real numbers, you get another real number. When you subtract two real numbers, you get a real number. When you multiply, you always get a real number, but not when you divide. And the main example for that would be if you divide like 5 divided by 0, that's undefined, right? So that's your counter example. This is why, right, not division. Okay, tomorrow we're going to do some more practice with making sure everybody knows which property is which and talk about closure a little more. But that's it for now, aside from you filling in the middle of page 14 where it asks you for a couple more examples of each of the three main properties: associative, commutative, and distributive. Thanks for listening.